We've mentioned the concept of additive models when we talked about factors, when we added a numeric covariate, and when we added a second factor to the model. In this module, we're going to go into more detail about additive models and about the opposite of an additive model, which is an interaction model. So the main thing to understand, the main concept, is what is an effect. So an effect of a covariate is the impact that changing the covariate has on the expected response. So the way we actually think about the effects is going to depend on which type of covariate we have. So if we have a numeric covariate, the effect of that covariate is, we could say it's summarized by the slope parameter. So the slope tells us how much the expected response changes per unit change in the numeric covariate. So that's kind of easy to understand. You could draw a picture of a slope, so on and so forth. Now, factor covariate is not much more complicated, but the effect, we can't talk about a slope because a factor is not a continuous variable. It's this qualitative variable with different levels. So when we talk about effects of a factor, we're talking about the difference in expected response from one level to another. So in the previous module, we talked about the parameter b2 minus b1 tells us how much changing the level of the factor from level 1 to level 2 impacts the expected response. Okay, now we're equipped to talk about the concept of additivity. A model with multiple covariates is called additive if the effect of each covariate does not depend on the values of the other variables or other covariates. So we'll look at some examples of that, but if you want like a one-sentence summary of what additivity means and how we're using the term in this course, is that each of the covariates has effects, and those effects don't depend on the values of the other covariates. So we'll go into an example in a minute. A model has an interaction between two variables if the effect of one variable depends on the value of the other variable. So by definition, a model that has an interaction is not additive. So we can think of interactions as the opposite of additive. So to see how this works, I think it's best to just look at an example and show what we mean by that. So we've already gone through this example, but we're going to do it again to illustrate this point. So here the response is going to be 3 p.m. temperature. The factor variable is city. We'll just say it has 2 levels. The numeric covariate is 7 a.m. temperature in the same city on the same day. And the factor-numeric model we wrote down in the last module this is a model for the response. Capital YI is B0 plus B sub J of I. J of I is the variable which tells us which level the factor is, which city in this case, plus C0 XI plus epsilon I. And I didn't write it here, but our assumption on the epsilons is that they're independent normals, all with the same variance. Now let's see why we call this an additive model according to our definition. So I'm going to try to keep the model formula right here. So the effect of the 7 a.m. temperature, since this is a numeric covariate, is the slope, which in this case is C0. That's the parameter that multiplies xi, which is the 7 a.m. temperature. So we're going to imagine we have the first 2 observations. We can write down the expected value of those 2. Let's say the first 2 observations are both from city 1. That means B sub J of I is B1 in both cases. So expected value Y1 is B0 plus B1 plus C0 X1. Expected value Y2 is B0 plus B1 plus C0 X2. And if we look at the difference of these 2, the only thing that changes is the value of the 7 a.m. temperature. It's the same city, but you change the 7 a.m. temperature. If we look at the difference between them, B0s cancel, B1s cancel, and we get C0 times the quantity x2 minus x1. So the effect of changing the 7 a.m. temperature by x2 minus x1, so as you move from the first observation to the second, you change the 7 a.m. temperature by this amount, is to change the expected response by the slope times that amount. That's just how slopes work. Namely, the effect of changing the 7 a.m. temperature did not depend on which city we chose. So we chose city 1, but there's no information about which city appears here. If we had repeated this and instead assumed that we were in city 2, the B2s would still cancel and the effect would be the same. So we get the same effect no matter if we're in city 1 or city 2, which means that the effect of changing 7 a.m. temperature does not depend on the city, and therefore this is an additive model in city and 7 a.m. temperature. Let's look at the other way around, the effect of changing the city. And in this case, we're going to hold the 7 a.m. temperature constant. And to just make this even more concrete, I'm going to give you the 7 a.m. temperature is 47 degrees Fahrenheit. So the third observation is from city 1. It has 7 a.m. temperature 47. The fourth observation is from city 2, and it also has 7 a.m. temperature 47. So we're holding that constant and just changing the city. If we look at the difference of the expected values, B0s cancel. You get B2 minus B1. And this will cancel as well because we held 7 a.m. temperature constant. And we get the effect is B2 minus B1. Namely, this doesn't depend on the particular 7 a.m. temperature we chose for this example. If we had picked 7 a.m. temperature to be 54 for both of these cities, they would still cancel and you would still get B2 minus B1. So the effect of changing the city while holding 7 a.m. temperature constant is B2 minus B1, which does not depend on the particular value of 7 a.m. temperature that we held constant. Now we'll see for the interaction model that this is not going to be true. It seems like, if you look at this, it seems like, well, obviously this will have to be true, but for the interaction model, it turns out that it's not true. And let's go through the math to see why. So here's our first interaction model. This is a different model. We have yi equals b0 plus b sub j of I. That's the same as it was before. But now the slope is different. The slope is going to be c0 plus c sub j of I times xi plus epsilon I. So j of I means the same thing here as it does here. This just indicates which city you're in for the ith observation. And you can already see from this that something's different. And the thing that you can see is different is that the slope depends on the city. So that's your first clue that this is not going to be an additive model. But let's go through the math and let's see what happens. So let's first look at the first two observations, and I'm going to assign a specific value to the 7 a.m. temperatures. We'll say that the first observation had 52, the second had 54. These are both from city 1. And let's look at the difference between these two observations. So this is, if we're thinking about what this difference represents, it's the effect of changing the 7 a.m. temperature by 2 degrees in city 1. We look at that difference, we get C0 plus C1 times 2, because that cancels, and these don't cancel. So it's going to be C0 plus C1 times 2. All right, now let's go to a different pair of observations, 5 and 6. And we're constructing this example so that now we're in city 2. So we get B2 and C2 here. But we've changed the 7 a.m. temperature by 2 degrees. As before in these two observations. So we can think of this comparison as the effect of changing 7 a.m. temperature by 2 degrees when you're in city 2 instead of city 1. So let's take the difference. That'll cancel, and we're left with 2 times C0 plus C2. Okay, if we compare these two differences, now in the first city, the effect of changing it by 2 degrees is to change the expected response by C0 plus C1 times 2. And here it's something different. The effect of changing the response by 2 degrees in city 2 is C0 plus C2 times 2. So we conclude from this that the effect of changing the temperature, 7 a.m. temperature, on the expected response depends on which city you're in. And that is the defining feature of having an interaction between city and 7 a.m. temperature. So just to summarize here, in city 1, the effect of 7 a.m. temperature, which is the slope, it's C0 plus C1. And in city 2, it's different. It's C0 plus C2. All right, so that looks at how the effect of changing 7 a.m. temperature depends on the city. You can also flip things around and look at the effect of changing city and how that depends on the 7 a.m. temperature. So this will always happen when you have an interaction, meaning that, for example, the effect of 7 a.m. temperature depends on city. The opposite's always going to be true, that the effect of changing city depends on 7 a.m. temperature. So let's look at Y3 and Y4. This is the same example as before. Here we're holding 7 a.m. temperature constant, but we're changing the city. And if we take this difference, so we view this as the effect of changing city when the 7 a.m. temperature is 47. So if we look at that difference, we're going to get what survives is B0 minus B2 minus B1. C0 is going to, C0 times 47 will cancel, but C2 minus C1 times 47 will not. So we get B2 minus B1 plus C2 minus C1 times 47. So in particular, that 7 a.m. temperature showed up in the formula for this difference, for this effect. Meaning that if the 7 a.m. temperature were 54 instead of 47, then we would have a different effect. Therefore, the effect of changing city in this model depends on the value of the 7 a.m. temperature, and therefore it's an interaction model. So you can check either way, whether the effect of city depends on 7 a.m. temperature or the effect of 7 a.m. temperature depends on city, to verify that it is an interaction. Okay. Now, this is an example. I think this is the most straightforward type of interaction. It's a factor-numeric interaction model, called that for obvious reasons. We can also have interactions between two numeric covariates. We call that numeric-numeric interactions. And we can also have interactions between two factors, and we call that factor-factor interactions, or two-factor interactions. So let's look at the factor-numeric interactions in general. So here we did a specific example, but now we're going to look at a more general form. So here the factor has j levels, capital J, and the model is the following. And the way you interpret this is that each of these capital J levels gets its own regression line. So the intercept for the kth level is going to be B0 plus BK, and the slope for the kth level is going to be C0 plus CK. So this is different from the factor-numeric additive model in that now the slopes depend on the level, whereas in the additive model it was just the intercepts that depended on the level. So if we think of the model in this way, we can reason about what the model degrees of freedom should be. Essentially, you have j levels, and for each of the j levels, you can specify what that line is as a function of the numeric covariate with two numbers, an intercept and a slope. So there has to be 2 times j model degrees of freedom. Now, if we just count up the parameters, there's going to be 2 times j plus 2. So there's B1 up to Bj, so that's j of them. There's C1 up to Cj, that's another j, so that's 2j, plus C0 plus B0. So there are 2j plus 2 parameters, and therefore when we form the design matrix, it's not going to be full rank, and we're going to have to do something about that to fit the model. In R, the way they solve the normal equations is that they'll use the drop column method. And the default in R is to set B1 to 0 and C1 to 0, which is equivalent to dropping the column for the intercept for the first level and the slope for the first level. So given this information, as an exercise, what I'd like you to do here is pause the video and try to complete this exercise. So, state the reduced model, the full model, the null hypothesis in terms of parameters, and give the degrees of freedom in the f-test that compares the factor-numeric additive model to the factor-numeric interaction model. So above we gave the factor-numeric interaction model. We talked already about the factor-numeric additive model. So if you were going to do an f-test to compare those two models, we have to state the reduced model and the full model. That's what's given to you. State the null hypothesis in terms of the parameters in the models, and give all the degrees of freedom for the f-test to actually carry out this f-test. So what I recommend is pause the video, write that out, and then unpause it, and the answer will come immediately after. So here's the answer. This is the factor-numeric additive model. B0 plus Bji plus C0 xi plus epsilon I. If I'm being really complete, I need to give the assumptions about the epsilon I, so I would get a point off for this answer here. The full model is the one above, so this is B0 plus Bji plus C0 plus Cji times xi plus epsilon I. Now the null hypothesis, this is how you go from getting the full model to the reduced model, is if you set all of these things equal to each other, you get back the reduced model. Now one minor quirk caveat is that you could also set them, the more obvious answer is that you set all of these equal to 0, because that just makes this term go away, and then it looks exactly like this model. Turns out that this is an equivalent assumption, and that's because the model is over-parameterized. The design matrix is more than full rank. Now the numerator degrees of freedom is going to be the difference between the two model degrees of freedom. So that's 2j minus j plus 1, which is j minus 1. And the denominator degrees of freedom is n minus 2j. This is just the residual degrees of freedom for the full model. Okay, so that's how you construct factor-numeric interaction model in general, and if you wanted to do the f-test, this is how you set it up. So the next thing I want to talk about are factor-factor interactions. So obviously in this case we're going to have two factors. Factor 1 is indicated by j of I. That tells us the level of the first factor for the ith observation, and we have capital J levels. Factor 2 we indicate with k of I. That tells us the level of the second factor for the ith observation, and that has capital K levels. And we write out the model in the following form. yi is b0 plus b sub j of I plus c sub k of I plus bc ji ki plus epsilon I. And again, I should write out the assumptions for epsilon I, which is normal 0 sigma squared, independent. Now this notation may look a little strange. All we mean by this, and we'll write these out in a second, is that this is a parameter. So this is a single parameter, which is why we put it inside of these quotations here. So it's not like we're taking the product of B and C. This is just notation for a parameter that is indexed by the level of the first factor and the level of the second factor. to see what I mean by that, let's just look at an example here. And this example is going to have j equals 2 and k equals 3. So since there are 2 levels of the first factor and 3 levels of the second, we can write out all of the expected values for each of the 6 combinations in a 2 by 3 table or array. And if we just take that model formula and write out the answers, we get for the 1 entry, first level of both factors, b0 plus b1 plus c1 plus, and this is what I mean, this is just a single parameter, bc11. So it's a parameter that has 2 subscripts. The 2 entries, b0 plus b2 plus c1 plus a different parameter, bc21. So each of these individual tables, cells of the table, the lowercase j, lowercase k entry is going to be b0 plus bj plus ck plus bcjk. So the interpretation of this model is that for these 2 factors, there are capital J times capital K possible combinations of its 2 levels, and each combination gets its own unrestricted expected value. Now, I use the word unrestricted to draw a contrast from the 2-factor additive model. In the 2-factor additive model, there are restrictions on how these cells of the table are related to one another. For example, in the 2-factor additive model, the difference between this cell and this cell is the same as the difference between this cell and this cell. For the interaction model, that is not true. So you have enough parameters here so that you have the full unrestricted capability to set any cell equal to any number. So there are no restrictions on the values of the expected values in the 2-factor interaction model. Okay, so let's think through what the model degrees of freedom has to be. Again, you can work this out by forming a design matrix and figuring out what its rank is. So it is useful to go through that exercise on your own, but we're just going to reason through and come up with an answer here. So since there are j times k cells and each gets its own unrestricted expected value, you could parameterize this model with j times k numbers, just the expected value for each of the cells. So that has to be the model degrees of freedom. That's the amount of freedom you have in specifying the expected values. Now, if you count up all the parameters, it gets a little wild. You have b0, you have, so that's 1. You have the b sub j's, there are j of those. You have the c sub k's, there are capital K of those. And then you have the bcjk's, and there are j times k of those. So this is way over parameterized. It's over parameterized by 1 plus capital J plus capital K things. Now, you have to make a decision when you fit the model of what constraint you're going to impose so that you can do the calculations. In R, the default constraint sets every parameter that has a 1 subscript equal to 0. So what do I mean by that? If we look up at the table, we just look at all of these parameters, and if you see a 1 in the subscript, it sets it to 0. So in this first cell, the 1, 1 cell, B1 is set to 0, C1 is set to 0, and BC11 is set to 0. This one, B1 is set to 0, C2 doesn't have a 1, so it's not set to 0. BC12 has a 1, so it is set to 0. So you look through all the parameters, any parameter that has a 1 in either of its subscripts is set to 0. Writing them out all out here is just the following. So if you apply that constraint to this table above, you get this table below. So keep in mind, we have not changed the model at all. We've just imposed a constraint on the parameters so that the design matrix will have full rank. So this is the same exact model. But now, since it's not over-parameterized, we can interpret the individual parameters. So if you look through, you can kind of come up with some interpretations for these parameters. So B0 obviously is interpreted as the expected value when both factors are at its first level. C2 is just the difference between this cell and this cell. So this is the effect of changing the second factor from 1 to 2 when the first factor is 1. And then you can go through and kind of come up with interpretations for each of the parameters. All right, so but first thing I want to do is look at why is this an interaction model? So we already looked at this comparison between this cell and this cell. So if y2 has this combination of the factors and y1 has this combination, so y2 is here, y1 is here. If we take the difference between those, like I said, we get C2. Now, if we take the difference of y4 is here, so this is 1, 2, 3, 4. So this is y3, that's y4. If we take the difference, expected value y4 minus expected value y3, the b0 plus b2 will cancel, and we're left with c2 plus bc22. So what we've just computed is the first one. This is the effect of changing from level 1 to level 2 of the second factor when the first factor is at level 1. That's this comparison here. The second comparison, y4 minus y3, this is the effect of changing the level of factor 2 from 1 to 2 when the level of factor 1 is 2. So that's the comparison between this cell and this cell. Now, like I said, in the additive model, these are the same. They're assumed to be the same. In the interaction model, they're not, because we have this additional term, BC22. So if BC22 were 0, then they would be the same, but the model has this in it, so it allows that the difference between these to be non-zero. If we look at another comparison, it actually ends up having the same parameters show up. So if we compare y3 to y1, we're comparing this cell to this cell. And the difference between those is b2. What does this measure? It measures the effect of changing the first factor from 1 to 2 when the second factor is at its first level. So that's this comparison. If we look at this comparison, this is y4 minus y2, according to this table here. Take the difference, we get b2 plus bc22. What it's measuring is the effect of changing the first factor from 1 to 2 when the second factor is at its level 2. And again, we see that the effect of changing the first factor from 1 to 2 depends on the value or the level of the second factor, and that is the hallmark or the defining characteristic of an interaction model. And it depends on it because there's this additional parameter, BC22. So like I said, in the additive model, there's no interaction. So a no interaction means that the difference between this difference and this difference is 0. That's the same thing as saying that this difference is equal to this difference. So no interaction means that those differences are the same, which means that the difference of the differences is 0. Now, if we calculate what's the difference of the differences, so y4 minus y2, that's this one, so that's BC plus BC22. y3 minus y1 is this one, so that's B2. If we take the difference between these differences, we're left with BC22. So BC22 is the parameter that tells us whether or not there's an interaction between the two factors at levels 1 and 2 for both factors. So this is why when we talk about interactions in two-factor models, we're talking about difference of differences. And then we won't cover this, but if you go up to like when you have 3 factors and you look at 3-factor interactions, you're going to be talking about differences of differences of differences. Okay, so let's look at degrees of freedom. And this is a nice heuristic to help you remember what the degrees of freedom are. In the interaction model, it's j times k. Each cell of the table has its own unrestricted expected value. In the additive model, like we said before, it's j plus k minus 1. And the thing to help you remember what the degrees of freedom for the additive model is that if you have all the information from the first row and the first column, that allows you to fill out the rest of the table. And if you just count up the number of cells in the first row and the first column, it's j plus k minus 1. So if you go to do an F-test to compare the additive model to the interaction model, you're going to need to know the difference in the degrees of freedom, model degrees of freedom for these two models. So if you just take the difference, you get jk minus j minus k plus 1. And it turns out you can factor this nicely as j minus 1 times k minus 1. And then if you stare at the table, this makes perfect sense. So the additional information in the interaction model is that these cells don't depend on the other cells at all. And if you just count up the number of those cells, it's going to be j minus 1 times k minus 1. So I think this table or this little diagram is a useful way to remember what the difference is between the additive and the interaction two-factor models and how to count up the model degrees of freedom. The third type of interaction we'll talk about are interactions between two numeric covariates. So here we have xi1 is the first numeric covariate, xi2 is the second, and the response is yi, lowercase yi, and our model for lowercase yi is capital Yi. And we can write the numeric interaction model as the following: b0 plus b1 xi1 plus b2 xi2 plus b3 times the product xi1 xi2 plus epsilon I. And epsilons are independent normals. Now this, even though this doesn't look like the form for a multiple linear model because we have a coefficient multiplying two covariates, or the product of two covariates, if we just define xi3 to be the product of xi1 and xi2, we can write down, then it is a multiple linear model. Now, for example, if we had this design matrix, this is the column of ones for the intercept. This is the column for xi1, just for this example. This is the column for xi2. And then xi3 is simply the product. So 3 times 5 is 15, 4 times 1 is 4, so on and so forth. Now what makes this an interaction model is, again, that the effect of one variable depends on the other. Now the easiest way to see this is to group terms so that we're writing the expected value as a linear function of one of the variables. So here I just notice I have a typo. This is expected value yi, so this should not have an epsilon on the end. So it should just be these two terms. So if we look at those two terms, we have b0 plus b2 xi2 plus b1 plus b3 xi2 times xi1. So this is the same exact formula as before, but we've just grouped the terms so we have a part that doesn't depend on xi1 and a part that does depend on xi1, and I've factored out everything that multiplies xi1. So we can think of this as a linear function of xi1, where this is the intercept and this is the slope. The slope would be b1 plus b3 xi2. So just writing both of those things out, we see that, remember, we defined the effect of xi1 as the slope. That is how much the expected value of yi changes when you change xi1 by 1 unit. So the slope is b1 plus b3 xi2, and this slope depends on xi2. Namely, it's a linear function of xi2. So because the slope, which is the effect of xi1, depends on xi2, this is an interaction model. We can rearrange things in the opposite way to write it as a linear function of xi2. So this intercept here is b0 plus b1 xi1. And the slope is b1 plus b3 xi1. So here again, the slope depends on the other variable, which in this case is xi1. So further evidence that this is an interaction model. Now, when you fit interaction models, I really encourage you to try to write out, to pick values for the one covariate, say the average of the values of the covariate, and write out what that linear function is. That can be a useful way to interpret the coefficients. It's often not easy to come up with a standalone interpretation for B3, but it is easy to come up with an interpretation for this intercept and this slope, and to think about how it depends on the other variable. Okay, our typo is fixed here. So now this should be the correct expression for expected value of yi here and here. So just remember, these are the same formulas. It's just we're rearranging the terms in a way that allows us to think about what the model is doing. All right, so another model, which I guess is not technically an interaction model, is quadratic models, but I like to think of this as an interaction, and I'll show you why. So here's the quadratic model. So you have one covariate xi1, and you want to write down a quadratic function, the expected value of yi being a quadratic function of xi1. You'd write the following: yi equals b0 plus b1 xi1 plus b2 xi1 squared plus epsilon I. Now this, at first glance, does not look like a multiple linear model because this term has a square in it. But if we just define xi2 to be the second covariate and equal to xi1 squared, then it's just b2 xi2, and that looks like any other multiple linear model with two variables. Now, the reason I say we can think of this as an interaction model is based on our definition of interaction, meaning that the effect of one variable depends on the other. We can think of this as an interaction between xi1 and itself. I say that because if we pick a specific value for xi1, so here this curved line is our quadratic, looks like any old quadratic, that the effect of changing xi1 when it's equal to a, this value here, is to decrease the expected value. However, because the quadratic curves, if we look at xi1 equals to b over here, the effect of changing xi1 is to increase the expected value from here. So this is the reason I say we can think of it as an interaction with itself, because the effect of xi1 depends on the value of xi1. Here it has a negative effect of increasing xi1, and here it has a positive effect. So let's say a little bit about interpretations for the parameters in this model. So this is all review of your algebra course, probably in 8th grade or in high school. If we look at, let me try to get this all on the same page. If we look at B0, this is just the expected value of yi when xi1 is 0. So if we set xi1 to 0 and look at expected value yi, we get 0. So this is where the point that the expected value crosses this axis here. So that one is kind of easy to interpret. If we look at the derivative of the expected value of yi with respect to xi1, we get the following. B0 goes away. We get b1 plus 2b2 xi1. So here, this is the derivative. And so again, this is another way of seeing that the slope, which we think of as the effect, depends on xi1. And this is the exact way that it depends on xi1. So with this form in mind, we can think of b1. This is the slope of the expected value curve at xi1 equals 0. So if we know, for example, that b1 is negative, that can kind of give us a picture in our head of what the quadratic looks like, that at 0 it's pointing downwards. Now that doesn't give us all the information. We need to know what happens after that. And B2 helps us get the rest of that information. B2 tells us whether the quadratic, expected value of yi, is concave up or concave down. So in this case, in this example here, B2 would be positive. So if we knew B1 was negative and B2 is positive, we know that the quadratic is going to be sloping down at 0, but then eventually it's going to come back up. And another piece of useful information from these coefficients is the location of the maximum of the minimum. So by that I mean where along the xi1 axis does the quadratic attain its minimum if it's concave up, or its maximum if it's concave down. And that formula, as you remember, is just minus b1 over 2b2. Negative, if you remember the mnemonic, negative b over 2a. That's just this in terms of the notation we've chosen for the quadratic. All right, and then you could take this further. You can write down polynomial models. So you can define yi is the sum j equals 0 to p of bj xi to the j power. Here you would just define, this also is a multiple linear model, if you just define x sub I sub j as x sub I to the j power. So this works the same. Interpretation of the coefficients becomes a little bit more complicated, but if you can always just plot out what the estimated polynomial looks like to get an idea of it. Lastly, I'd like to talk about models that have quadratic effects in two variables. So the model I'm going to write down here has two covariates, xi1 and xi2. And this model I'm going to call the full quadratic model. And it's the following formula. I won't read out all the terms, but you can see that it has this, what we called before, the interaction term, xi1, xi2. It also has xi1 squared and xi2 squared. And I'm using a slightly different notation. This helps us keep track of which coefficient corresponds to what. So b12 is the coefficient that multiplies xi1 times xi2. b11 is the coefficient that multiplies xi1 squared, and b22 is the same for xi2. Now again, it's going to be helpful to rearrange terms in the equation to figure out what's going on. So if we group this into terms that depend on xi1, we can write down expected value of yi as this quadratic. Here, the entire equation is the formula for yi, and expected value of yi is just these first three terms. So here is the part that doesn't depend on xi1. This is the part that enters linearly into xi1, and this is the part that enters with a quadratic. So we can think of this as a quadratic for each value of xi2. This is a quadratic function of xi1, and this is the intercept. This is the coefficient on the linear part, and this is the quadratic coefficient. So that just means we can think of this as a quadratic function of xi1, but the particular shape of the quadratic function depends on what the value of xi2 is. So this is an interaction term, an interaction model. We could do the same thing for xi2. So this would be the intercept in the quadratic formula for xi2. This is the linear term, and this is the quadratic term. Now I said that this is an interaction model, but if b12 is 0, then this term goes away, and we can think of this as an additive model because now the effect of xi1 is contained in this information, b1, which tells us the linear part, and b11, which tells us the quadratic part. And neither of those depend on xi2 if b12 is 0. So we can think of this as an additive model in xi1 and xi2 if b12 is 0. It's not a linear additive model, it would be a quadratic additive model. But if b12 is not 0, then the linear part depends on the other variable, and it is an interaction model. One reason for writing out the coefficients in slightly different notation is that we can write this model in terms of matrix vector multiplications. And this is going to make it easier for us to generalize this to more than two variables. So if you look at this formula is the exact same as this formula up here. So there's b0, and then we have the dot product between xi1, xi2, and b1, b2. So this will give us these two terms. And then we have this quadratic form. So this is a quadratic form in xi1 and xi2 with this particular coefficient matrix. So if you do this matrix multiplication and multiply it by 1/2, you'll see that you get these three terms out of here. In particular, this is a symmetric matrix. It has b12 on the lower part and the upper part. So this notation for the model helps us to extend this to more than two variables. Essentially what we do is we have xi1, xi2 up to xip, b1, b2 down to bp, and then this thing becomes a p by p matrix. So that's what's given in this formula here. So b0 plus xi transpose. So xi is a vector which contains xi1, xi2, xi3 up to xip. And b is a vector which contains b1, b2, b3 up to bp. Here, capital B is a matrix whose ij entry is bij. And then we can write out the entire quadratic in p variables in this form here. So this model I just mentioned because this actually is a really useful model in some applications where you have a bunch of variables and you want to try to figure out what is the optimum value for the variables, the xi1 up to xip, that gives you the highest expected value of yi. And if this B matrix is positive definite, then you can actually extract that maximal value, I should say optimal value, because it could be a maximum or a minimum. It's a minimum if this matrix is negative definite. Then you can extract that optimal value. So this is really useful in people use this kind of model in industrial applications where they're trying to optimize some sort of industrial process that depends on a bunch of different variables. Now you can write out what that optimal value is. If you take the gradient of the expected value of yi, this just means take the partial derivative of expected value of yi with respect to each xij and put them in a vector. And then you have to set that equal to 0. So the gradient is this thing, b plus little b plus big B times x. If you set that equal to 0, then the optimal value is going to be x star equals minus b inverse lowercase b.